viewers, welcome to CEC lectures. Myself Dr. Preeti Jalwani from Department of Computer Science, Aryavat College, University of Delhi. In our present series of operating system concepts, in the previous lecture we have started with the problem of classical problems of synchronization, and within that classical problem of synchronization we have seen one problem which was known as producer consumer problem, or that is also known as bounded buffer problem. And we have seen what is the structure of this producer problem, and let us try to recap it quickly and then we will move forward in this problem. So till this point we have seen that there are kind of two processes, one is producer, another one is consumer. Producer is producing some items and which are being consumed by consumer. So these are the processes which are working in coordination with each other. Now here comes the scene of synchronization, because they must be in kind of synchronized scenario, because the consumer should not consume the process which is not being produced by the producer. And what could be the structure of the producer and the consumer problem? Let us try to recap that as well quickly. That is, the producer is going to produce one particular item, but this will not be produced, or this will not be stored inside the buffer if my buffer is full. And what is the situation of full buffer? The full buffer situation is going to be tested with the help of the pointer in, which says in plus 1 mod buffer size equals to out. So while this is situation which is going on, the producer is going to do nothing. Even after producer has produced one item, this is going to be stored inside the buffer array at the location in only when the this is available. This is available as in buffer is not full. Till the point buffer is full, it is not going to do anything. So do nothing situation is there. And after kind of storing the next produced in buffer in, the in will be incremented. Similarly, if we have a look at the consumer process, that is, while in equals to out, that means the buffer is empty, nothing to be consumed, it is in the do nothing state. And then whenever it is having an item to be consumed, that is to be stored inside the variable next consumed, and the value of the out pointer or the out index, we can say, is increased. So with this structure of consumer and producer process, we have seen what are the problems in this in this situation. So first limitation here is this scheme is allowing at most buffer size minus 1 items in the buffer at the same time. So simultaneously, whatever number of whatever the size of buffer is, you can only store buffer size minus 1 items in the buffer at one point of time. Another issue which is not being addressed with the proposed structure of producer and consumer problems is about that the if the producer and consumer problems are attempting to access the shared buffer concurrently, then these structures will not be able to handle that particular situation. So that means we need to modify the algorithm in order to take up this situation, or in order to solve this problem. So what could be the possible solution? One possibility is to add an integer variable in the name of, let us say, counter. Initially this is to be initialized as a 0. Counter is going to be incremented every time we see a new item. If that new item is being added to the buffer, the counter is incremented, and it is decremented every time we remove one item from the buffer. So one additional integer variable counter is to be kind of, we can say, included. And let's see the how this code for the producer process is going to be changed from the previous one. So the new code is given on the screen, which says while true, that means while this is going on, the producer is producing a next item, and we have seen that counter equals to buffer size. That means this is the situation where your buffer is full and despite of producing, the producer is not able to store that particular data item inside the buffer, because counter equals to buffer size. So, this is the situation where your buffer is full. So, till this situation, for the time till this situation persists, the situation is of do nothing. And if it is kind of, let us say, if we have something to store, that means some space is available, then the item produced is going to be stored inside the in pointer or inside the in index in the buffer array. In will be incremented as it was done before according to the rules of circular array, and obviously we need not to forget the increment, need not to forget to increment the value of the counter, because one more item has been produced. So, whenever the producer is producing item, the counter is going to be increased. Whenever there is a consumer which is going to consume the item from the buffer size, the counter will be decreased. So, similarly what all can be the changes inside the consumer process, that is shown on the screen, which says while true, while counter is equals to 0. So, counter equals to 0, that means it is having nothing. So, it is in the do nothing state. So, that means consumer is not having anything to be consumed. Now, in both the processes, that is in the consumer as well as in the producer process, now the situation of buffer full and buffer empty is depending on the counter. It is not depending upon the indexes in and out, if we can see this clearly. The in the producer problem, the counter equals to buffer size is an indication of the buffer full, and counter equals to 0 is the indication of the empty buffer in case of an consumer problem. So, if the buffer is empty, it is in the do nothing situation, otherwise it will take out something from the buffer and it is going to give it this to the next consumed variable, increment the value of out this thing, and decrement the counter as well, because the counter has to be decremented one item has been consumed. So, this is the situation which is going to solve the problem which we were saying that in the earlier version what was happening, the only number of items which can be stored was equals to buffer size minus 1. So, now that has been taken care here with these modifications in the producer and consumer problems. We can now store the number of items which is essentially equals to the buffer size as which is equals to the buffer size by making these some corrections, or by we can say introducing one variable which is in the name of the counter. Now, although one problem has been solved, the producer and the consumer routines shown above are correct separately. They may not function when they are executed concurrently. So, that means producer is also in execution, and so as in the consumer. What will happen, that there will be a condition which is named as race condition, and we have also seen this race condition in the previous lectures, that the two processes, which is the producer and the consumer, are trying to access and manipulate the same data. Which data I am talking about is essentially the buffer, or more specifically we can say the value of counter. The value of counter is going to be incremented by producer, and the value of counter is going to be decremented by the consumer. So, let us say there are 3 instances of producer, 3 instances of consumer. So, if we if it is going to happen like producer consumer, then producer consumer, then producer consumer, value of the counter variable is going to be different, or it is going to happen like producer, 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 then consumer, consumer, consumer. So, the value of counter variable is going to be different. What I am trying to tell you, that this is a race condition in which the value or the outcome of the execution depends on the particular order in which the access takes place. If it takes place in producer consumer pair thrice, or it is going to take place all the producers first and all the consumers on top of it, then it is going to give me a different outcome of the execution, which is the value of the counter variable, and this condition is known as a race condition. Now, race condition is there. So, what are we going to do to guard or to protect our system against this race condition? In order to prevent this race condition or in order to prevent this inconsistency, we need to ensure that only one process at a time should be manipulating the variable counter. So, either the producer process or the consumer process will be manipulating the variable counter. In order to have such a situation or in order to implement such a solution, we need the processes to be synchronized in some ways. Now, here is a problem. We have seen that the synchronization is required. Now, what all could be the solution towards this is, so before going into the implementation of solution for the producer as well as the consumer problems, we need to see some background of these solutions. These solutions is, the solution actually lies with the concept of mutex locks, which is actually a software tools to solve the critical section problem. Now, the problem which we are discussing is producer consumer problem is giving us the race condition, or because inside the critical two processes are allowed to enter into the critical section at the same time. So, in order to solve the critical section problem with the help of software sites, we need some software tools, and the simplest of these tools is the mutex locks. So, mutex locks is a lock which is there to protect the critical region, and when the critical region is prevented, the race condition will not happen. So, that means a process must acquire a lock before entering into a critical section, and it will release the lock when it is going to exit from the critical section. So, in order to take the lock, the acquire function will be there, and in order to release the lock, the function release will be there, and this mutex locks is actually a Boolean variable whose value indicates whether the lock is available or not. If the lock is available, then we can call the acquire function. If the lock is not available, then we cannot call the acquire function, and vice versa. The lock is considered unavailable when we cannot or when the call to the acquire is going to be failed, and a process that attempts to acquire an unavailable lock is blocked until the lock is released. So, that process has to be has to wait while the lock is released. So, in order to release the lock, we have a release function, and in order to acquire a lock, we have an acquire function, and here is the code of acquire function, which says while not available, it is kind of do nothing in a state or busy waiting, we can say, and we will also say this available equals to false, that means it is not available. So, this is what the acquire is. Then we come to how this acquire is going to take place. So, before entering into the critical section, acquire lock will happen. So, if acquire lock succeeded, that means the process has blocked the process has taken up the value of lock, or process has taken the charge of lock, and no other process will be allowed to enter into the critical section if the lock is till the lock is not released. So, there is acquire lock, then we have critical section, the process in the critical section, and after completion of the critical section, the lock will be released, and critical section, as you all are aware, that it is followed by a remainder section, and this will go on while the situations are true. Similarly, if we see the definition of the release or the code of the release is nothing but that says available is equals to true. So, it is now the your we can say lock is available, while in the acquire where we have seen the lock is not available because it has been acquired by someone else. So, when the process is going to acquire a lock, it will say for the next upcoming request the availability is false, and this availability will be set to true whenever this release has been called. So, this acquire lock is being called before the critical section, the process into the critical section afterwards. So, because of this lock thing, because this lock is not having an open value or a value which can be taken by someone else, so no one can enter into the critical section unless this lock is released. Now, coming to the kind of integration of this particular mutex locks into the problem which we were considering as the producer consumer problem. So, producer consumer problem when taken up with the help of this mutex locks. So, here as I have already told you that the algorithmic solution which we are going to take are implemented with the help of semaphores here. So, what will be the structure of producer consumer process, or what all data variables these producer consumer processes will kind of having is, one is the integer n, which is about the number of we can say whatever is number of elements in the buffer array we can say. Then we have one semaphore which is mutex and the present value is 1. Then we have semaphore empty where the value is equals to n, and then we have semaphore full where the value is 0. So, these data variables will be we can say used by the producer and consumer problem, which is one integer n and 3 semaphores. One is the mutex, another one is empty, and third one is the full. So, mutex is having value 1, empty is having value n, and full is having value 0. So, basically what are we assuming here is our buffer or our pool is consisting of n elements, or the pool is consisting of n buffers, where each buffer is capable of holding one item. So, that is why we have taken integer n, and presently all these buffers or all these elements are empty. So, we have set the value of semaphore empty as n. So, semaphore empty n is equals to n means all the buffers are available, all the buffers are empty, and the mutex semaphore provides mutual exclusion for accesses to the buffer pool and is initialized to the value 0. So, this mutex is the semaphore, that is the we can say a variable, that is the lock variable which is going to provide the access for mutual exclusion to the buffer pool and is initialized to value 1. Apart from this, we have two more variables or two more semaphores, which is empty and full. So, empty is there to count or keep count of number of empty buffers, and full, as the name indicates, is the we can say variable which is keeping the count of full buffers. So, here we have integer n, which is the total number of buffers, then we have semaphore which is empty, the number of buffers which is empty, then we have full semaphore, the number of buffers which is occupied, which is full already, and one semaphore which is mutex in order to provide the access rights for a particular process. And semaphore empty is initialized to n, and semaphore full is initialized to value 0, that we have seen. Now, with these four structures in hand, which is integer n, then we have mutex equals to 1, empty equals to n, and full equals to 0. Let us try to see what all we can say possible changes can be there in the structure of producer and consumer processes, so that the problem of the concurrent access can be we can say solved. So, in order to solve that problem of concurrent access, which was earlier in the which was present earlier when we were structuring the producer and the consumer process without any semaphore, was the problem of synchronization. That means, if producer and consumer both the codes are running simultaneously, then there may be a rest condition, and this rest condition is for the updation of the variable counter. So, that is going to affect the final outcome. So, in order to solve that problem here, we have restructured the producer process as it is shown on the screen, and within this restructuring what is being introduced is two calls, one is wait and another one is signal. So, wait is there in order to hold, and the signal is kind of that the semaphore is available. So, when an item has been produced by the producer process, the empty and the mutex, both the variables are going into the wait condition. That means they are in the situation that no one else can acquire these things, acquire these variables, these semaphores which are empty and mutex. So, that means in a way we have logged these two variables, and then the next produced item is being added to the buffer. Now, after the addition of the next item into the buffer, the process producer process is done with its work. So, that so now the mutex has been kind of treated with the help of signal function call, which is we can say is kind of released, and so as the full, and this will go on, this will keep on doing as as long as producer is producing. Similarly, when we talk about the changes in the structure of the consumer process, so consumer process is a process which is going to remove an item from the buffer, and that will be stored inside the next consumed. So, this is going to mark the wait condition for the mutex semaphore and for the full semaphore. That means, before starting any kind of taking up data item, taking up exercise, it is going to log, one is the full semaphore, another one is the mutex semaphore. That means no other process is going to acquire the mutex, or we can say no other process is going to acquire the access rights, we can say here. So, and also the full also the value of full is under the lock provisions. So, we have wait full and wait mutex. Then by seizing or by freezing these two semaphores, or by freezing these two variables, an item has been removed from the buffer, it is stored in the next consumed. Now, the task of the consumer process is over. That means the process that means we can say the item has been consumed and the value of the variables has been increased as it should be. After that, there is something which is kind of we can say signal, which is about the release of these metaphors. So, whatever we know the signal is, one is the release which is mutex. That means now other processes can take up this mutex things, and also the empty semaphore has been called under the signal function called, and this will also keep on going till the point you have items to be consumed. So, with the help of wait and signal, and with the help of or we can say with the help of treatment of the semaphore full, mutex and empty along with wait and signal in the producer and the consumer problems, we are able to solve the situation of or we are able to solve the problem of the synchronization inside the your producer consumer problems. So, in this lecture, let us recap what we have done. In this lecture, we have started with the recap of what is the producer consumer problem, what is the structure of producer and consumer processes, then what are the problems here, and then we have started with the introduction of one variable counter, which is going to remove one limitation of number of items equals to buffer size minus 1. That solution we have seen, but even with that, if the producer and consumer problems are accessing the shared buffer concurrently, this will end up in a race, this may end up in a race condition. So, in order to prevent that race condition, we have used semaphores as full, mutex and empty. With the help of these semaphores, these 3 semaphores are treated with the weight and the signal function calls, and we have implemented the structure of producer and consumer processes, so that even if these producer and consumer processes are working simultaneously, there will be no inconsistency in the data, there will be no synchronization problem. And here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed it. Thank you for a patient hearing.